en los Estados Unidos de Norteamérica. Voy a hacer una lectura de lo que ha sido su desarrollo profesional y empezaré por mencionar que actualmente es el director de diseño de puentes de la compañía Arup, con sede en San Francisco, California. Rafael Manzanarez tiene más de 35 años de experiencia, tanto en el diseño de puentes de gran escala, así como en la rehabilitación de puentes complejos. Fue director del Instituto Americano de Puentes Segmentales, conocida por sus siglas en inglés, que es ASBI, entre los años 1996 y 2010, y miembro del comité que desarrolló las normas AASHTO para el diseño de puentes en dovelas prefabricadas postensadas. Participó también en varios comités para el desarrollo y actualización de las normas AASHTO para diseño de puentes. Recibió el Premio de Excelencia en Ingeniería por el Instituto ASBI, que ya mencioné antes, en el año 2000. Recibió también el Premio Arthur Wellington en el año 2004 de la Sociedad Americana de Ingenieros Civiles por el diseño del puente de suspensión sobre la bahía de San Francisco. Es el puente nuevo, conocido como el autoanclado, ahí en San Francisco, California. Este puente ganó el premio de la estructura de excelencia del Instituto Mundial de Ingenieros de Puentes en el año 2015 por las innovaciones de ingeniería sísmica implementadas para cumplir con requisitos rigurosos para el diseño sísmico en condiciones geológicas variables y complejas. Como director técnico, Rafael dirigió los diseños de puentes importantes y complejos que incluyen el Gerald Desmond sobre el puerto de Long Beach, California, también el nuevo puente de la bahía San Francisco-Oakland, los puentes segmentales para trenes en la línea verde del metro de Los Ángeles, California, el reforzamiento antisísmico y contravientos del puente Golden Gate en San Francisco, California. Realizó el diseño preliminar del puente entre Hong Kong, Shanghái, Macao, en China, de 35 kilómetros de largo, con 3 puentes atirantados sobre los canales de navegación, entre otros. Además, destacan dentro de sus proyectos los premiados puentes Centenario, es el segundo cruce del Canal de Panamá, en Panamá. También el puente sobre el río Sable en Vancouver, Canadá. El del estrecho de Carquines de Benicia a Martínez en California. El puente atirantado Port Mann en Vancouver, Canadá, y el viaducto North Halawa en Hawái. Sus diseños incluyen proyectos en varios países como Australia, China, India, México, Colombia, Perú, Panamá, Costa Rica, Ecuador, Brasil, Estados Unidos, Venezuela y otros. En México, sus trabajos también incluyen la ingeniería de construcción de los puentes El Zapote y el Quetzalapa en la carretera México-Acapulco. Actualmente dirige el diseño de la pasarela para peatones ciclistas en el puente de suspensión de la bahía de San Francisco y el diseño del puente sobre el río Zitzaola que une Costa Rica con Panamá. Rafael ha dado clases sobre diseño de puentes en las universidades de Stanford, en Berkeley, San Diego, Guayaquil y el Politécnico de Monterrey en California. Asimismo, ha escrito y presentado artículos técnicos sobre puentes de la Sociedad Americana de Ingenieros Civiles y sobre ASBI, que ya mencioné antes qué significa, entre otros trabajos. Rafael, por favor, te invito a pasar.
Gracias. Muchas gracias, Jorge. El Politécnico de Monterrey está en México.
Perdón. Es que hay dos.
La vieja California, the old California. Ok. Yo voy a hacer la presentación en inglés, porque la puedo hacer más rápido. Tengo bastantes diapositivas. Y la presentación va basada en 3 proyectos prácticamente. El énfasis va a ser el diseño sísmico, la ingeniería sísmica y por qué diseñamos estos puentes para ingeniería sísmica. Voy a pasar acá. Los proyectos son, este es el mapa de California que muestra las fallas que tenemos en California. Aquí está la bahía de San Francisco, el puente de Benicia Martínez Bridge, el de San Francisco Oakland Bay Bridge y el de Gerald Desmond Bridge aquí en Long Beach, al sur de California. No sé si esto funciona. Como que no está funcionando. Bueno. ¿Cómo funciona? Ok, ahí está. Entonces, como ven en el mapa, as you see in the map, we have a lot of faults in California. Most of these faults are strike slip faults that break sideways. So the magnitude of the earthquakes are not very large, but they are strong. They are short duration and they are very strong. So I'm going to talk about these 3 bridges with the emphasis, as I said, on the seismic design. But also I want to also talk about the construction and the complexity of some of these projects and what we have to do to make sure we meet the very strict design criteria for what we call lifeline structures, which is structures that have to be functional after the major earthquake for passage of emergency vehicles like fire trucks and ambulances the day after the earthquake. So that's the key criteria for us to meet. So this is the viaduct of the Benicia Martinez Bridge over the Carquinez Strait. You can see over here. The Bay Area is over here. This is the existing bridge, the railway bridge, and the existing highway bridge. In this case, they needed a new bridge for this lifeline structure. It's a highway, Interstate 680, I'm sorry. So we designed this viaduct. And the design was compared against other designs, such as cable stay bridge, multi-span cable stay bridges, steel truss bridge, and a steel box girder bridge. And this came out to be the least expensive option. Some of the unique parts about this bridge is that it's a five-lane highway structure, but it also needs to accommodate a bar train system, which is our local relatively heavy train system on one side of the deck. So the deck is 25 meters wide. We use a box cutter section. The span lengths are about 220 meters, and the depth of the girder is about 11.4. What is significant about this bridge is that we use high-strength, lightweight concrete for the superstructure to reduce the mass that we have to design the foundation for. Foundations are very difficult at this site with very long, large diameter piles, steel pipe piles, composite with concrete. We also use, because of such a wide box, in this case we use ribs every segment so that the slab actually spans in the longitudinal direction. The other interesting thing about this project is that the foundations are very tricky at this site. One of the things that we learn about this job is that you need to have more than one boring in some cases, even within one footing. The footings are so large that one boring may not be enough to indicate exactly the rock profile that we have at the site. In this case, we learned a lesson that the rock profile was actually sloped, and we had some problems installing the steel pipe piles. So we had to pre-drill the hard soil, soft rock, so that before installing the pipe piles. But also the footings were precast. At least the shell of the footing, the majority of the footing was precast, and the rest of it was reinforced with post-tensioning tendons within the pile cap. And this is a picture of the pile cap with the opening for the piles. This is construction of the bridge, simultaneous span being built. The bridge is quite tall, and that's why we decided to go with lightweight concrete, high-strength lightweight concrete. That, by the way, we have to test the material of lightweight concrete and also normal weight concrete for these kind of long-span concrete bridges to make sure that we understand the actual creep characteristics and the shrinkage characteristic of the concrete mix we're going to be designing for. That's very important in this kind of long-span concrete bridges, that you test the concrete that you're going to be using during construction. We use a special lightweight concrete mix with stylite aggregates and actually normal weight sands, not lightweight sands. So this is a trick to make sure that you get the high-strength concrete in this kind of design. So in California, they don't like to use bearings. They like to use monolithic connections between the superstructure and the substructure. So in this case, all the connections are monolithic to the piers and to the substructure. This is the pier table shot. And here, once the pier table is built, the cantilever construction starts. So this is typical construction. The only difference about it, we're using normal weight concrete. This is a view of the form traveler from the top. The segments are 5 meters, typical segment length. The shot from the traveler from the bottom. And the shot inside of the forms of these travelers. And a picture of the cantilever. One of the cantilevers is already built. The forms are being taken down. And this is a picture of the hinge beams that you use actually a mid-span between the two cantilevers, between frames. So instead of putting the hinge points or expansion joints at every quarter span, which has typically been done, the reason why we put these mid-span hinges is an expansion joint is to, in case that we have significant damage on the bridge, the structure is still stable. It will not collapse on the dead load. That's one reason why we put mid-span hinges, hinges and joints at mid-span of the frames. Now I'm going to talk about this project that was just completed in 2013, the San Francisco-Oakland Bay Bridge in the Bay Area. It's actually the east span's replacement. This is a shot aerial view of the project. You can see San Francisco in the background. And this is the new bridge when it was being built. And this is the east spans of the San Francisco-Oakland Bay Bridge. So the limits of the project from the island called Yerba Buena Island here, all the way down to what we call the Oakland Touchdown. It's about 2.5 miles long. The structure carries 300,000 vehicles a day. So we have to maintain traffic on the bridge. Particularly, it was tricky in this area over here because this is a double-deck structure. We were going to replace this one with the side-by-side decks. So the Oakland Bay Bridge was built in 1936 for a cost of $77 million. It was built in 3 years and 4 months. Incredible. It was at that time the longest vehicular bridge, and it has the largest tunnel in the world here in the island. The seismicity, as you showed the map earlier, we have 2 major faults, the Hayward Fault and the San Andreas Fault. So we developed for this project 6 ground motion, 3 from each fault. Hayward Fault and the San Andreas Fault. The San Andreas Fault can generate magnitude earthquake of 8.1, and the Hayward Fault about 7.5. And this is where our bridge is, right between the two faults. So in 1989, we have a very short duration earthquake, 15 seconds, about 50 miles away, 70 kilometers away, and it still caused some damage in the Bay Area. The reason it caused a lot of damage is because the soil in this area here, in this area of the Bay Area, on the east side, we have very soft clays that amplify the ground motion. So PRE 9 of the east span collapse. So we had to deal with disruption of traffic for 30 days, and it was very, very difficult. So it was decided, instead of retrofitting that old bridge, to build a new one. Part of the reason was that the old bridge sits on very short wooden piles, about 80 feet, which is about 25 meters long piles. Basically, the bridge was floating in the bay mud, the young bay mud, very soft clays. So it was decided, instead of retrofitting that old bridge, to build a new one. So what kind of bridge? I'm going to explain a little bit about how we came up to the solution, and the aesthetic was a very important part of it. But basically, we have 4 different structures on the new facility: the Oakland approach structure, the Skyway Bridge, the main span bridge, and the transition bridge here on the island, on Yerba Buena Island. From the 2 side-by-side deck, we had to go into the tunnel, which is double deck. So the geology of the site dictates a lot about what happens to the design of the bridge. You see the island on the left. The rock profile is brown here. It's called the Francisca Formation. It rises up very quickly. So we have, the rock profile is very close to the surface on the west side of the project. But as you go towards Oakland, the profile drops down pretty quickly here and continues to drop. So we have soft bay mud, as we call it, John Bay mud, and then we have old bay mud, and then we have the Opera Alameda Formation, which is relatively dense sands. So we decided to actually tip the piles at this formation. Except the main span located in this location, we decided to actually put one tower, in this case, basically founded on the rock on one side, and the rest of the bridge, I'm going to explain to you what we decided to do on that one in just a minute. There was a competition. The client decided to ask for ideas. These are some of the crazy ideas that people came up with. Some are good, some are not so good. Incline tower, like this outside the deck. It was a very unique idea. The client said, no, we don't want an incline tower. On this project, we want a vertical tower. Or at least a taper tower, but basically no incline tower. They also did not want this kind of design, diamond-shaped towers. Don't ask me why, I don't know why. Anyway, these are some of the ideas that came up. The client couldn't make up their minds, so they decided to hire a consultant. That was the consultant I used to work for, T.Y. Lin. And they gave us this criteria that we needed to work with: vertical tower, uniform design, twin parallel decks. The tower height was limited to the height of the suspension tower on the west span, and no diamond-shaped towers. And they wanted a cable-supported structure over the navigational channel. 150-year design life, which is rather unique. Usually we design for 75 years in the United States, so we have to accommodate 150-year lives. So that means that we have to actually upgrade the design criteria, the earthquake risk, the wind risk. Everything was updated or increased to accommodate this 150-year design life. So, clear sequence of yielding damage in overload condition. We always have to look at what happens if the earthquake is, say, 25% higher than what you actually assume in your risk. So we also have to look at that condition. 1.25 times the actual design earthquake to see, is the bridge going to collapse or not? What kind of damage are you going to see? So we have to look at that. No inspection or repair at inaccessible location. This is very important. That means that whatever damage, which is repairable, in this case, you need to allow traffic to go on that bridge the next day after the major earthquake, so it has to be repairable. So that means that any plastic hinging or any damage to the structure has to happen above the water, in this case, at the pier locations. So we have to control that damage by providing proper ductility to the design. So reduce maintenance and repair because of the 150-year life. Reduce the number of joints and bearings, protect the cable, and visual consistency was also an important criteria. So many designs we came up with, and these are some of the options that were actually carried on to a 30% design level to make a decision to go forward. This is a cable stay bridge design with a single tower, with the stay cables splayed out. And this is a view, three-dimensional view of that design. This is another view of what we call a suspension bridge, but in this case, it's not your typical suspension bridge. It's what we call a self-anchor suspension bridge, where the cables are actually connected to the deck. They're not anchored to a rock anchor location, because we did not have rock 150 meters down below the water surface. So that's where the decision was made to, if we go to suspension bridge, it should be a self-anchor suspension bridge. So these are the two options that were carried to 30% design, with confidence that we can make this design work for seismic, meet all the seismic criteria, all the design criteria. So the self-anchor suspension bridge with a single tower in the middle, and the cable stay bridge also with a single tower in the middle, a concrete tower for the cable stay, a steel tower for the suspension span. And the reason why the suspension span actually was the one that was selected by my client and by this EDAP committee that was set up by the client is because of the similarity of that design and the proportions of that design to the rest of the bridges in the Bay Area, the suspension spans in the Bay Area, the West Span over here, and the Golden Gate Bridge in the background. Particularly the West Span, just about similar to the proportions of this bridge. Similar tower height, similar size span, and similar center span. The rest of it, there's no similarity whatsoever. So that's the design that was selected. This part of the project, a pedestrian path was added to the project after the design was selected, so we have to accommodate that pedestrian bicycle path 5 meters wide on one side of the structure on the south side. So that created some problems, but manageable. Now, this is the difficult part of the project. It's not just the main bridge and so on, it's the fact that we have to bring traffic into the tunnel that has a double deck. So we have to use the existing structure, the double deck structure. So eventually we build a detour structure on this side, put traffic on that side, take down the old bridge, and erect the rest of the structure on YBI. So I'm going to talk about this design of the self-anchor suspension bridge. It has a main span of 385 meters, which is half of the span of the west span of the Bay Bridge. The tower T1 is anchored on the rock on pipe piles, steel pipe piles. This is the west pier, called the W2 pier. This is an anchor pier, and this is the pier E2. The expansion joint with the skyway is at this location, so that we can maintain the span length that we have on the skyway at 160 meters. So the proportions you can see over here, the bridge is not symmetrical for dead or live load, so we have to do something on the backspan, and I'll talk to you about that in just a minute. In plan view, the tower is in the center, single tower, but actually 4 shafts, and the cable goes around like this, and is anchored at the east end of the bridge. Cable is anchored within the box girder. The 2 decks are connected with cross beams that are the space at about 30 meters on center. So the deck is not connected to the tower. As you can see over here, it's actually floating around the tower. We wanted to make sure that the inertia of the superstructure were actually taken by the 2-side pier, the W2 and E2 pier. And longitudinally, most of it goes actually into the pier in the island, which is the shortest pier. So you can see the elevation of the tower with 2 shafts in this direction and 2 shafts in the longitudinal direction, and the shafts are connected by what we call shear links. The shear links are steel members that actually can yield when the tower begins to move and creates high shears in the short shear links that they can be replaced if they get damaged. The cross-section of the tower, pentagonal shape over here, a steel section stiffened with plates. And again, they're connected with shear links, as you can see here in the plan view. This is a view of the shear links. They are bolted. The interesting thing about the shear links, we use 70 KSI steel on this side and 50 KSI steel on this side to make sure that the section yields in this location, and then this piece can be replaced if it gets damaged. Tower foundation is very interesting. They are steel boxes that are connected to the steel piles by means of plates that are welded in the field. So it is filled with concrete, lightweight concrete, but the concrete basically is just to maintain buckling stability within the steel plates. 13 piles, 60-meter long, 2.5-meter diameters. The top of the piles are filled with concrete, and the pile caps are fairly large. So this is a view of the cross-section of the deck. Two box girder, 5.5 meters deep, 25 meters wide, and then again, on the south side, we're carrying the bike path, a 5-meter path on this side, a pedestrian bicycle path. And this is the cross beam. This is a view of typical floor beam of one of the boxes. And the deck, we use orthotropic deck with this kind of arrangement, V shape, with cutouts with this shape. One of the things we have to make sure we comply with is compactness. Because this is a self-anchor suspension bridge, the cable force at the ends are actually compressing the entire deck. So we're going to make sure under the seismic event we don't have any buckling problems. So that's why we did this. So the effects of compactness are shown over here. It limits the plates and wall slenderness, and the plates may be a little bit thicker in some cases. The cable, we only have one suspension cable that actually loops around the west pier like this. I'm going to show some more detail. This is the west pier, which is a concrete section, post-tension. And the reason for the concrete I'll explain to you in just a minute. This is a model of the cap beam. And here we're connecting the steel box to the concrete section of the pier cap by means of post-tension and tendons between the steel and the concrete. This is the east pier elevation, quite different from the west pier. It's connected together because in this case the steel box is restrained by, of course, we have restrained shear keys, steel shear keys to the cap beam, and these are your bearings, rocker type bearings. This is a view of the east pier and the foundation, again steel pile caps with steel piles. This is a view of the E2 during construction. Now this is a 3D view of the cable. Again, it's a single cable that is anchored at the east end. It comes up to the tower, goes back around the pier EW, and it comes back over the tower, and then it's come back down and it's anchored here at the east end of the eastbound deck. Number of wires, 18,137 strands, 127 wires per strand. So this is a 3D view of the cable as it comes down over the deviation saddle of the west pier. One big saddle. We're concerned about the construction of this cable, but it was done very well by the contractor, American Bridge, and by Fujian Cable in China. And this is what we call a jacking saddle. We wanted to make sure that the cable force is compensated as we erect the deck by jacking the cable at this end as we put weight on the cable through the suspenders. Cross-section of the cable, one strand is galvanized wire, high-strength strands. So we went all the way to create 1,850 MPa steel for this wire. And we protected it with zinc outside and with the X-wire wrapping. The S-wire wrapping is a new technology that came out from Japan, where the S-wire protects the moisture intrusion by providing some sort of a locking mechanism between the wires. So we also provided dehumidification to the cable by providing dry air at certain entry points in the cable bands of the cable, and also at the top of the tower and at the deviation of the cable saddles. So the construction of this bridge is unique in that you have to erect the deck, you have to have the deck in place before you erect the cable. It's the other way around as a normal suspension bridge. So how do you erect the deck? You can use false work, you can use stay cables, but in this case the contractor used false work to erect the deck and then install the cable and then transfer the load from these false board towers into the cable and the tower and so on. Tower saddle, very large, came in 3 pieces from Japan. And here is the main cable, the deviation saddle at the east pier, because the cable has to come back into the deck of the box girder. Seismic performance, I talked already about this. But what I wanted to say over here, to balance the dead load, in case that there is damage to this pier, significant damage to this pier, for example, then we added this counterweight. Basically, the pier cap here is a counterweight that balances the vertical reaction that we get from the reaction of the cable due to the unbalanced span at the other end. You can see over here the cable force is about 200 meganewtons that have to pre-compress the steel section of the box from end to end. So these are some of the reactions that you see on the bridge. Perform time history analysis for the entire bridge itself, including skyway, all the connecting structures. Shear link has to be tested. How am I doing with time? Yeah, okay. University of Nevada, Reno, we had to proof test some of these unique designs, and it was done. It took some time to do that, but I'm glad we did it. We were able to then use the results of this test in our computer model to confirm the analysis that was done. Seismic displacement demands in the order of 1.3 meters at the tower, transversely, and 1 meter longitudinally, and over here about 1 meter in both directions at the east pier. This pier over here is quite stiff, so it takes somewhat less displacement. This is where we expect the yielding to occur in the shear links in the tower, and perhaps here at the west bend, W2, so we have to design for the ductility of this tower and the piers, and likewise at E2 at the base. So you have to understand the mechanism where the yielding could occur on these structures, and that way you can design appropriately for those demands. So a proof testing program included wind tunnel, tower shear links, the west pier, and the orthotropic deck. Here is the full aeroelastic model being done of the bridge at the West Wind Lab in Monterey, California, by John Raggett, who passed away just a couple of months ago. The tower shear links were tested as well. And these are the results, these pictures of the test. The demands was 0.12 radians. We have to meet the demand. This is the cyclic behavior of the shear links. So we got quite a bit of ductility out of the links so they can yield and carry the energy. PRW2 test was also tested at a scale 1 to 4 at UC, University of California, San Diego. So with these actuators, the pier is over here with the proper reinforcement, and it was jacked continuously until we deflected the pier to the maximum capacities. So we use this result to correlate to our design, and that's how we designed the structure. This is the cyclic behavior of that pier with a proper confinement design, steel confinement, with mechanical splice hoops confinement, by the way, not spiral. So that's something else that we have to deal with in California, which I think is important. We also have to test the stability of the deck during the cyclic load, the movement of the deck up and down, 0.5 meters during the seismic event, and of course the compression on the deck. So we did test the ribs, the top deck, particularly we're concerned about. You can see it over here, a section. This was done at the University of California of San Diego. And cyclic testing was done, and a panel buckle, like this. And we found out the buckling capacity, and we designed for it. And here it is the axial load displacement of this element. So the SE event will carry us to this point, so we have some capacity left beyond the SE event, so we are okay. Pile driving construction of the tower. So large piles. This is the pile cap of the E2 footing. This footing were fabricated in Texas, brought in by barge to the Panama Canal to California. And you can see over here the openings for the plates that are going to connect the piles that go inside this element here. once the piles are driven through the pile cap. So all steel design, all steel construction. So here is the section of the tower at the site. The tower footing is being lowered with this catamaran device that was used also to erect the rest of the foundations of the skyway, which are also steel cap and steel piles. We like to use in California epoxy rebar, which we call it purple color, which is for corrosion protection. The Pier W2 is constructed. And here the tower lift 1 being fabricated in China. That's another thing we have to deal with. If there is any federal money on the project, the steel has to come from the United States. So you have to go through a process. The steel could not be made in the United States because there is no capabilities in the United States to do this kind of fabrication. We have to get waivers from the federal government to be able to go outside the United States to build any piece of steel. So that takes a long time. And on top of that, you get penalized for doing that by about 20% of the cost. So this is a steel box section also fabricated in China, in Shanghai, by ZPMZ. Tower section being lifted by this large crane that was used to erect the box girder. And here it is the tower legs coming in barge. The bottom part of it is here, that's the top, being lifted with this frame that is between the box section. Is being lifted and it's basically on some rail on this barge itself. As the tower gets lifted, this point gets moved to there. That's another view of the tower being erected, and you can see the false work for the deck. One of the tower legs is in place. Once the tower legs, the 4 legs are here, this frame here is actually erected up, and then to pick up the next lift of the tower from this heavy lift equipment sitting there. So another view of the tower being erected, tower legs. Here are the box girder being transported. These are the site, and they use this floating crane. That's another issue here in the United States. This floating crane here has to be made, the whole of the crane has to be made in the United States. It's what they call the Jones Act. So this barge was actually, the bottom of it, the hull, was actually taken to China and refurbished, and they made it into what you see over here. That's the only way this kind of floating cranes can actually go into the waters of the United States. So there it is, being lifted into the false work support, in place there, and then the cable, once the deck is all erected, the cable comes prefabricated with their own sockets, like this. This is mounted at these reels are mounted at the east end of the bridge, and they're reeled from here to the tower, and it goes around the deviation saddle. In this case, we shape the strand like this in a square shape so that we make sure that it passes through the saddle. And here is being reeled towards the tower. You see a picture of the cable, the strands. And you see the cable bands are very important to keep the shape of the strands during construction and during erection and before compaction. And here the cable is being compacted with this compacting machine. The load transfer from the false work to the cable was very difficult. The cable moved 10 meters sideways, 3 meters down. So the exact location or orientation of the cable bands is very important in this kind of construction and design. So we have to check that very carefully, look at the construction sequence, how many suspenders were going to be jacked so that we know exactly how to orient the cable bands beforehand. So here is a picture of the bridge completed at the end of 2013. This is the main bridge. Now I'll go a little bit to the skyway. How am I doing with time? Okay? Okay. The skyway section, basically 4 frames. We're trying to avoid joints. So some of these frames are very large, about 700 meters long, and expansion joints, as I said, are here, a mid-span between the piers. Foundation, tricky foundation. So I show you the piles are 100 meters long, 2.5 meter diameter steel pipe piles, with wall thicknesses of 65 millimeters at the top and 50 millimeters at the bottom. We botted the pile slightly, and the reason we did this, we wanted to control the permanent set of the bridge, limit the permanent set, because the soil, the soft soil is going to plastify and it's not coming back. So we limited the displacement of the deck to 6 inches, which is 150 millimeters. So that was the criteria that was set. So we botted the pile 1 to 12, and we were able to limit that permanent set of the bridge by doing this. So I think this is very important consideration in design for soft soil. People say you should not be battering pile in seismic earthquake, but actually we proved that it was the best solution. Skyway structure, precast segmental, 160 meter span. Never had been done before in California in a high seismic area. We don't think so. So we have to do some proof tests of some of these elements. In this case, the segment joint between the segment, the precast segment, has to be proof tested. This is the cross section, the typical section, 25 meters wide. This is the box. Actually, we had a struts over here. The rest of it is actually non-structural. It's lightweight concrete. It was designed to carry light rail system. And here is the bike path, which is a steel section. This is the typical cantilever, pier table, about 20 meters. Its segment length about 8 meters. And precast construction. So we tested the joints. There was a lot of concern about the behavior of the joints during the seismic event, because the structure do move, the superstructure does actually move quite a bit. So we tested the joints at UC San Diego. Precast joint, no rebar across joints, only post-tensioning. And to our surprise, the best solution came out to be all external tendons. Gave us the highest utility as compared to all internal tendons, or a combination of both internal and external tendons within the concrete of the box section. In our case, we didn't have any tendons except the tendons within the cantilever and the bottom tendons. So we felt satisfied. We met that requirement of the demands for at this joint, some of these joints during the seismic event. The post-tensioning system, the cantilever tendons. Again, the pier, table, the superstructure is monolithically connected to the pier. Here's the rebar that was used for the cage construction of prefabricated offsite, set in place here into this opening within the steel box of the foundation. Precast construction was done about 70 kilometers away from the site. You can see over here the precasting machine. There were actually 4 long beds were used by the contractor, in this case Kiwi Pacific, and the construction of the segments is ongoing. There are a special fabrication for hinge segments and other segments. And here is the construction of one of the segments with transverse post-tensioning, tendons being installed, concreting of the segment. Very complicated joint at the expansion where we have the hinge beams. So you have to really look at three-dimensional drawings, in this case, to make sure you avoid conflict. It's a post-tensioning. The segment's being transported to the storage site. And then from there, this is a storage site. You take him to the barge transported about, as I say, 70 kilometers away over the river and then over the bay. And then once the pier tables are done, the segments are erected with this, fairly simple lifting mechanism here, which is a steel beam anchored at the back with post-tensioning rods. The segment weights are, some of them are 850 tons. Steel hinge beams. Yeah. Okay. Interesting thing about this beam, mid-expansion joint, we have to make sure that we fuse the steel pipe. The steel pipe can actually carry, it's very long, 20 meters long. It can carry shear moments at the joint in any direction. So we have this design, and we want to make sure we yield it with a 50 KSI steel in that section. And here's a picture of of that steel beam. We have 2 per box. Here is a view of the rendering of the bridge. And since I completed my presentation, next time I come, I'll give you a presentation of the Gerald Desmond Bridge replacement project in Long Beach. Thank you. Thank you.